Let's talk about equilibria for different reaction classes. In this chapter, we'll majorly be focusing on equilibria for insoluble compounds. So this essentially brings us to the topic of solubility. Hopefully you guys remember what solubility means. It's another term for dissolution. So if a compound or salt, ionic specifically, dissolves in a given solvent, we call it soluble compound. And if it does not dissolve in it, it's called as an insoluble compound. So solubility is essentially defined as the number of grams of a solute dissolved in 1 liter of a saturated solution at a given temperature. So whenever we take a solute, we add it to a particular kind of solvent at a specific temperature and create a saturated solution, which means that there is no more salt that can be dissolved into that particular solvent without it precipitating out. That is called as solubility. Usually it's given in the units of grams per liter. Hopefully this table right here are the solubility rules. Hopefully they ring a bell for you guys. It tells you which compounds are soluble and which ionic compounds are usually insoluble. For instance, all the nitrates are regarded as soluble compounds. There are no exceptions to it. All the acetates are soluble. Most of the halides, including chlorides, bromides, iodides, are soluble, and the exceptions are silver, mercury, and lead. So essentially, whenever we see a silver chloride, silver bromide, silver iodide, or same thing with mercury or lead, most of those compounds are insoluble. Same thing is true for sulfates. Most of the sulfates are soluble except for some exceptions which are listed right here, including strontium, barium, mercury, and lead. And this right here at the bottom tells you all the compounds that are insoluble. So most of the sulfides, carbonates, phosphates, hydroxides are insoluble. And here are some of the exceptions to it, such that if all the sulfides are regarded as insoluble except ammonium sulfide and alkali metal sulfide. So only ammonium sulfide and alkali metal sulfides are the ones that are soluble, and includes calcium, strontium, and barium. So these are some of the exceptions to the insoluble ionic compounds, which are usually insoluble. So when we say a compound is insoluble, what does that mean? So we take, let's say this is an example where I have a solvent. In this case, my solvent is water. All right, so I'm going to write right here. So the molecules that you see right here are the molecules of water. Okay, so in this case, my solvent is water, and this particular salt right here, let's say, is AgCl. So if we go back to our solubility rules, you would know that AgCl is an insoluble compound, right? Which means this does not dissolve in water. So if it does not dissolve in water, we call it insoluble. But up until now, we have been saying that whenever we have an insoluble salt, it does not dissolve in water. But that's not true. Most of the times, these insoluble compounds dissolve in the solution, in solvent, but very sparingly. So they're very sparingly soluble, meaning they do dissolve, but the extent is really small. Okay, so what you see right here is the complete solid AgCl, which is not dissolving in water. And what you see right here, some of this AgCl, you can see right here in this picture, some of the AgCl has started to dissolve. And this essentially creates an equilibrium between the amount of salt that is not dissolved and the amount of salt that is dissolved. This equilibrium is what we are going to be focusing on. So whenever we say that a salt, an insoluble salt, is dissolved in water, we are essentially saying that they are sparingly soluble or very slightly soluble, and there is an equilibrium that exists between the amount of solute ions and the amount of aqueous ions, right? And this equilibrium, the equilibrium constant for this particular equilibria is called as the solubility product constant, or Ksp. Sp stands for the solubility product and K is the equilibrium constant. So going back, like you guys have seen these reactions in equilibria a lot. So in this case, the equilibria is between solid AgCl, so the solid right here, and the ions, which is Ag ion and chloride ions that have dissolved. So AgCl solid will dissolve into water to produce Ag plus ions and Cl minus ions. So it gives its cations and anions. This, whenever we write the equilibria for this is going to be, you remember, equilibrium constant is always products over reactants, right? So concentration of product in this case is going to be Ag plus times the second product, which is Cl minus, and both of them exponents are 1. Why? Because you can see the stoichiometric coefficient is 1 in this case, and divided by the reactants. But in this case, the reactants are solid. So if you remember, we never include solids in our equilibrium constant expression. So this is the equilibrium constant expression whenever we are talking about solubility of an insoluble salt. And this equilibrium constant essentially is called as solubility product because this is specific towards the solubility equilibria of our particular salt of interest. All right, so whenever we have to write this Ksp of a particular salt, that's how you would figure out what is the Ksp of that salt. So for instance, if the question is, can you figure out what is the Ksp for AgCl, or the expression for AgCl, that's what the expression is going to be. So it's always products over reactant, which is not included in this case since it's a solid, right? So whenever AgCl dissolves, it goes towards the right, which is towards the products. And if it does not dissolve, it's going to create what we call as precipitate, or the reaction is called as precipitation. So precipitation is essentially when we mix two solutions or liquids such that they produce a particular solid out. That process is called as precipitation, and the compound that solid that comes out or that falls out of the solution is called as the precipitate. All right, so for instance, if I mix a lot of Ag plus solution and Cl minus solution in water, at some point it will start precipitating out. I'll see some solid coming out of those liquid solutions, and that process is going to be called precipitation. So this equilibrium is essentially an equilibrium between dissolution of the salt and precipitation of that particular salt. All right, just like every other equilibrium reaction, we have seen there are two things that we usually compare. It's Q, which is called the ion product expression, and the Ksp, which is the equilibrium constant. So the same concept applies right here as well. Q is the ion product expression for slightly soluble ionic compounds at any given point in the reaction. So whenever any concentrations are given, if you plug in the values into the expression, that's going to give you value of Q. And if you have the concentration at equilibrium and you plug in the values into the expression, it's going to give you Ksp. So the same concept applies right here as well. So if there is a salt MpXQ, that essentially means the expression for Q for that particular salt is going to be M to the power of P constant times the concentration of X to the power of Q. All right. So MpXQ is going to, this is solid, is going to dissociate to give two ions, which is Pm plus Qx in this case. So concentration of M times P, which is the stoichiometric coefficient, concentration of X over, sorry, I meant exponent, not times, exponent Q, which is the stoichiometric coefficient for X. So this is same concept. It tells you if you're working with different salts. Oh, my bad. So let's pick a couple examples. That way we can actually see what we're talking about. So if I have a salt, let's say in this case MgF2 solid, what would be the expression for Ksp for this? Fairly simple. We can write it in the same manner. Ksp is going to be whatever is the product concentration. So it's going to be Mg Ksp equals concentration of Mg2 plus ion to the power of 1 because of the stoichiometric coefficient times concentration of fluoride ion to the power 2. So fluoride ion squared, right? There's another example which is Ag2CO3. So in this case, if we have a salt, silver carbonate, we know it's insoluble. What is its expression going to be? It's going to be concentration of silver ion squared times concentration of carbonate ion. Next salt example is calcium phosphate. So this is also an insoluble salt. It's going to dissociate to give us 3 calcium ions and 2 phosphate ions, right? So Ksp expression is going to be concentration of calcium ion cubed times concentration of phosphate ion squared, right? Now we saw the expression of comparing Q and comparing the Ksp, right? So what does the Q and Ksp comparison mean here? So it's the same concept. If I'm talking about Q and Ksp, we will be comparing the direction, the values of Q and Ksp, and that would tell us which direction would the reaction go. It's exactly same concept that we have learned in the chapter of chemical equilibrium. Whenever Q is less than Ksp, the reaction is going to go towards the products. Whenever Q is equal to Ksp, the reaction would be at equilibrium. Whenever Q will be greater than Ksp, the reaction is going to go in the reverse direction. All right. So whenever reaction goes in towards the right direction, that means salt is solubilizing, right? Dissolution, remember. And whenever it's going in the reverse direction, that essentially means the salt is going to produce more solid, meaning it's going to precipitate out of solution. So it's going to produce a precipitate. All right. So it's again written out right here for you guys. Whenever Q is less than Ksp, there is not going to be a precipitate. Whenever there is no precipitate, that means our solution is unsaturated. So if it still has the possibility that we can add more salt into the solution without it being precipitating out. Whenever Q is equal to the solubility product, it is going to be a saturated solution and the reaction is going to be at equilibrium. Whenever Q is greater than Ksp, it is going to produce a saturated or a super saturated solution, and it's going to produce more precipitate. Why? Because the reaction is going towards the left, towards the reactants. All right. Hopefully this makes sense. This is very similar concept as chemical equilibrium. Here's another example of another insoluble salt, which is lead fluoride. So if we take equilibrium constant or solubility product for lead fluoride, it's going to produce lead ion and 2 fluoride ions. So for every single lead ion, we will have 2 fluoride ions. Ksp is going to be concentration of lead times the concentration of fluoride squared. Okay, so here are some questions for you guys to try out. So for instance, if we are talking about magnesium carbonate, the question is asking write the ion product expression at equilibrium for each of these compounds. And there are 3 different compounds: magnesium carbonate, iron 2 hydroxide, and calcium phosphate. So hopefully you guys remember how you can go from name of an ionic compound to its formula. If not, let's quickly take a look. So if I have magnesium carbonate, quick review. Magnesium means what kind of ion is it going to produce? It belongs to magnesium, first of all, is the symbol is Mg, right? It belongs to which group? Group 2 in the periodic table. So it's going to produce a charge of 2 plus, right? That's the ion for magnesium. Carbonate, what's if you should be able to figure out what's the formula for carbonate ion. So it's going to be CO3 2 minus. So whenever you know the ions, if you guys remember, there's this rule of crisscrossing to figure out how many atoms of magnesium and how many carbonate anions do you need to neutralize the charge. Our aim is to neutralize the charge of the compound. So it's going to be magnesium 2, carbonate 2, and we divide this to get to the smallest number that we can get as the subscript. So it's going to be MgCO3. So this is going to be our compound. And once you have your formula, you want to confirm that your final charge is actually 0. So how many magnesium ions do we have? 1. What is the charge of each magnesium? Plus 2. So that's our cationic charge in total. What is the anionic charge in total? Carbonate. We have how many carbonate? We just have 1 carbonate ion. What is the charge of each carbonate anion? It's -2. So plus 2 and -2 are going to cancel each other out, and the complete charge of this compound is going to be 0. So we know that our formula is correct, right? Now this was kind of review from before. if you need help with this, you should go back to your previous lecture and previous topics to figure out how you can come up with the formula of a compound, ionic compound, if you're given the name of that compound, right? So magnesium carbonate, in this case, the question is what is the ion product expression? So we know the ion product expression for magnesium carbonate is going to be based on its equation, which is MgCO3, which is solid, is going to dissociate and create an equilibrium to produce magnesium 2+ ion, which is aqueous, plus carbonate ion, which is also aqueous. So our expression of Q is going to be concentration of magnesium 2+ ion times concentration of carbonate ion, right? That's our answer. Let's quickly try iron hydroxide, and then I'll leave you guys to try the other example. So formula for iron hydroxide, it is telling me ion is 2+. Why? Because this, whenever it gives you this number right here in Roman numerals in parentheses, it's telling you what charge the cation has. So this is ion 2+. Hydroxide ion is always OH minus, right? So crossing over the charges, that would give us a formula of Fe1 and OH whole twice, right? So let's confirm if our formula is correct or not. If our chemical formula is correct, how much total positive charge of cation do we have? We have 1 Fe ion, and each cation has a charge of +2, so that's my total +2 charge. What is my total negative charge in this compound? I have hydroxide ion. Each hydroxide ion has -1 charge, and I have 2 of those, so 2 times -1 would give me a total of -2. So this is my total negative, total positive. They cancel each other out. The charge of my final compound is 0, which means my formula is correct, right? So now how is this going to dissociate? If you want, you can do this in your head. If you practice it out, it will be easier to do this in your head. If not, you can always write down the formula, the reaction. Okay, so in this case, iron hydroxide is going to dissociate to give 1 Fe ion and 2 hydroxide ions. So my Ksp or Q expression, sorry, it's the product expression, is going to be concentration of iron ion times concentration of hydroxide ion squared because of my stoichiometric coefficient. So that's my final answer for this, right? I'll let you guys work with calcium phosphate. So please pause the video. You can work, figure out what's the formula for calcium phosphate, and then figure out what's the Ksp. Pause the video now. Okay. All right, so here is the answers. So hopefully you guys got the right answers this time and are familiar with how to figure out the Ksp of a particular salt. Now, same thing, what does the Ksp tell us about? What information does Ksp give us? It's telling us how soluble this particular insoluble salt is, right? Even though it's insoluble, it has a certain solubility. So what is the solubility of all of these compounds? So higher the Ksp, higher is the value of Ksp, more is going to be the solubility. So more ions it's going to produce, right? So if I have a salt, I'm going to go back to the example, the first example we saw, AgCl, solid dissociates to produce Ag ion and Cl minus ion, chloride ion. So this is dissolving. Higher Ksp means more products, so more dissolution, meaning more solubility. So if I give you a couple different salts and I ask you, can you tell me which salt is more soluble? You should be able to do that based on the Ksp value. Okay, but it is a little bit tricky because this solubility right here is another term. Let's see how we can calculate solubility of a salt if we know Ksp of that salt. Okay, so we saw already what's the definition of solubility. Solubility is essentially number of grams of solute dissolved in 1 liter of a saturated salt solution, right? Now there is another term which is called the molar solubility, which is more important in this case because molar solubility stands for the number of moles of solute dissolved in 1 liter of a saturated solution. So if you guys remember, in chemistry, we can never compare two different compounds in terms of grams. We always compare them in terms of moles, right? So that's why whenever we're talking about which salt has a higher solubility or which salt is more soluble, you will have to compare their molar solubilities, all right? Which is also given by capital S, and the unit is again molarity or moles per liter. Now, how do you figure out what is the molar solubility for a given salt? That's again coming back to our favorite concept in this whole concept of Equilibria, which is ice table. So if I take a particular salt, for instance, in this case, we're talking about calcium hydroxide. How can you prepare an ice table for it? Calcium hydroxide will dissociate to produce one calcium ion, and for each calcium ion, we are going to produce two hydroxide ions, right? So initially, in the beginning, again, this is a salt. It's solid, so we don't care about its numbers in chart of our ice table. Initial concentration of calcium ion is 0. Initial concentration of hydroxide is 0. Change. For up until now, we have been using X as a term. From now on, we will be using capital S, and that is what this molar solubility is. Okay, why capital S? Just so you are more, you can differentiate between X and capital S, and you know that capital S here stands for molar solubility. If you're comfortable with X, that works too. There's nothing, no difference here. Only difference is that now we are using the alphabet S as our change. That's it. Okay, and this S right here stands for molar solubility of our particular salt. Okay, so coming back to this, if change is going to be, these are products, so products are always plus. If it's this calcium ion is plus S, hydroxide, every calcium ion has two hydroxides. I know that from the stoichiometric coefficient, so this is going to be plus 2S, meaning at the end in equilibrium, I'm going to have S of calcium and 2S of hydroxide ion. So now I can write down the expression of Ksp. So Ksp for this is going to be concentration of calcium ion times concentration of hydroxide ion squared, right? Don't forget the square, and don't forget to put this 2 right here in 2s. That's the major mistake that most of the students make. So now we can just plug in our numbers right here. Calcium is S times, I'm going to times hydroxide ion, which is 2s, and again squared. So don't forget the square right here. Okay, so this would give you 4s cubed. So now my Ksp equals 4s cubed. So if I know the value of Ksp, I can figure out what is the value of S, which is the molar solubility of this particular salt. Hopefully this makes sense. Again, this is all written out in your PowerPoint as well. So you can see right here, this is all solved out in your PowerPoint as well. Okay. Now here is a table that will help you to practice all these concepts that we just talked about. So for instance, AgCl. This is telling you which compound we are interested in. This is telling you what is the expression for Ksp, what is the concentration of cation in this case, what is the concentration of anion that is going to be produced, and what would be the relationship between Ksp and S. So if you try to fill out this table for all of these salts, in the next slide you'll see all the answers to for all of these salts for all of these particular columns right here. So try to solve this by yourself and then compare your answers, and hopefully you don't run into any issues. Okay, let's try one of these salts here. So I'm gonna pick I'm gonna pick this particular salt right here, which is silver carbonate, right? So if I'm talking about Ag2CO3, if you feel comfortable, write down the equation for it, chemical reaction for it. If you are comfortable just doing this in your head, that's great as well. But make sure don't do too fast, okay? Don't go too fast. Don't forget any of these exponents. So silver carbonate is going to produce silver ion. Always remember silver has a charge of +1. Oh my god, if I can write +1, okay. And it's going to produce 2 cations in this case, right? There's 2 silver ions. plus 1 carbonate ion. For each 2 silver ions, it's going to produce 2 carbonate anions. So in this case, what would be my Ksp expression? Sorry, it's going to be right here, which is Ksp equals concentration of silver ion squared times concentration of carbonate ion to the power of 1. Right, so that's my expression for Ksp for this particular salt. Now the question is asking what would be the concentration of cation and concentration of anion at the end, meaning at equilibrium. How can we figure that out? If I want any concentrations, I need an ice table. Okay, again, this is a solid, so I do not consider it. Initially 0, 0. Now remember, you can work with X, whatever works for you, or you can work with S. I like to go with S because that just tells me this is molar solubility of this particular salt. So what would be the change here? The change is going to be positive since it's a product and it's being produced. And for silver, I see my stoichiometric coefficient is 2, so it's going to produce every dissolution of this, each mole of salt is going to produce 2 moles of silver ion, so it's going to be 2s. Again, carbonate is going to be S. So at equilibrium, I'm going to have 2s of this, so 0 plus 2s and 2s of this and s of this, right? So what is the concentration of cation at the end? Make this right here. Cation concentration is going to be 2s, and anion concentration is going to be s. And I'm going all the way. I'm only talking about this particular salt right here. Okay, this is the concentration of anion. So now the question is asking what is the relationship between Ksp and S? Fairly simple now. I know Ksp is, just plug in the values right here. Ksp is silver concentration squared. So silver is 2s. That's going to be 2s squared times carbonate concentration to the power of 1, which is S. So that is going to give me Ksp equals 4s cubed. So that is the relationship. This is cube. That is the relationship between Ksp and molar solubility. So if molar solubility is given to you, you can figure out what is Ksp. If Ksp is given to you in question, you can figure out what is molar solubility. Right? So now you can pause the video, try to solve all these terms, all these columns, fill out all the columns right here for each of these salts, and then you can unpause the video and go to the next slide, okay, and check for your answers. Right, I'm going to pull up the next slide now so you can confirm your answers right here. Okay, now let's, based on the same concept, let's try out some questions. This is telling you everything that we just did in words, how you can determine Ksp from solubility, how you can determine solubility from Ksp. Okay, let's try out a few questions. Lead sulfate is a key component in lead acid car batteries. Its solubility in water at 25 degrees Celsius is given to us. These many grams per ml solution. What is the Ksp of lead sulfate? So I know the salt that I'm talking about is right here, PbSO4, lead sulfate. The solubility is given to me. Again, this is not the molar solubility, so you should be able to identify the different solubility. The unit is in grams per ml. So solubility is 4.25 times 10 raised to power minus 3 grams in 100 ml of the solution, right? Question is, can you figure out what is the Ksp for this particular salt, right? Now, what do we know about Ksp? Whenever we need Ksp, let's write down the expression for the particular salt. PbSO4 is going to, it's a solid, insoluble, sorry. It's going to dissociate to give me Pb2 plus ion and sulfate 2 minus ion, right? How do I know 2 plus? There are a couple ways you can know. One is Pb2 plus because it's telling me in question. This is lead 2 sulfate. Second idea I know is that one lead ion is neutralizing one sulfate ion. What is the charge of a sulfate ion? SO4 2 minus. So I need, if I want to neutralize this particular charge, I need an ion which has a total charge of 2 plus, meaning my lead right here, which is only one atom, is going to be Pb 2 plus, right? Okay. So again, Ksp expression in this case is going to be concentration of lead ion times concentration of sulfate ion, right? Do I know the concentration of any of these? Not right now. So if I want to figure out Ksp, I need to figure out these concentrations, right? What is the one way that I can figure out these concentrations? I will probably have to make an ice table, first thing, right? Second thing is, what's given to me in the question is the solubility of this compound in grams per ml. So if I make an ice table, in an ice table for a particular salt, I know we are talking about molar solubility, which the unit for that is molar or moles per liter. The solubility that's given to me is in grams per ml. Is there a way that I can go from grams per ml to moles per liter? There is, right? So if I can convert these grams per ml from solubility, grams per ml to molar solubility, I would know, I would be able to figure out the concentration at equilibrium for lead and sulfate ions, and I can plug those in and figure out Ksp, right? So expression, or sorry, my ice table is going to look like this. Initially, I have 0 and 0. This is going to produce plus S, just 1 right here because the stoichiometric coefficients are 1 for both of these ions. So it's going to be S and S. And my Ksp is going to be S times S, meaning S squared, right? So if I can figure out S, I can figure out what is my value for Ksp. So how can we solve for S? Let's convert these grams per ml into moles per liter. How can we go from grams to moles? The relationship between grams and moles is molar mass, right? What is the molar mass of lead sulfate? For this, you'll have to go and use your periodic table. Sorry, my video got cut in the middle. So we were talking about how we can take lead molar mass of lead sulfate, right? So for molar mass, you would essentially just take mass of one lead, a mass of one lead atom plus mass of one sulfur plus mass of one oxygen times 4, right? Since we have 4 of those, that would give you a total mass of 303.3 grams. So that is the molar mass of our salt. So we know the relationship or the conversion factor that relates grams and moles is molar mass. So sorry, 1303.3 grams of lead sulfate is equal to 1 mole. And what's the conversion factor that relates ml to liters? We know that 1 liter is 1000 ml. So we'll use these conversion factors. I want to get rid of grams, so I'll divide it by grams. The other side is moles, so multiply by moles. 1 mole is 303.3 grams. So grams and grams will get cancelled. My final answer is moles per ml. Now let me convert ml to liters. So to cancel ml, since it's in the denominator, I'm going to have to multiply with ml, divide by liters. My conversion factor is 1 liter is 1000 ml. So ml and ml got cancelled, and I have my answer in moles per liter. And this would give you, sorry, I'm running out of space here. So this will give you right here solubility, molar solubility now in moles per liter, right? Of 1.4 times 10 raised to power minus 4 moles per liter. So that is the value of my capital S, which is molar solubility. So if this is molar solubility, I can plug this value into my expression for Ksp and calculate what is Ksp, right? So in this case, let me solve it right here. Ksp is going to be s squared. Let me separate this out. Ksp is s squared, so it's going to be 1.4 times 10 raised to power minus 4 squared. That is going to be our value of Ksp. Now remember, equilibrium constants do not have units, they are dimensionless quantity. So at the end, this is not going to have any units. Okay. And for the final numbers, here are the final numbers which are solved for you guys. So Ksp is 1.96 times 10 raised to power minus 8, right? All right, so now let's go back to the problem B from our question. This is a very similar concept, actually same concept. So I would just pause the video right here. You guys can work on this problem right here by yourself and then come back and look for the solution. And if you need explanation, you can look for the explanation given to you in the video. But pause the video right here and work on the question. So hopefully you guys have the answer for this question. Let's see how I'm going to attempt this question now. So when lead 2 fluoride is shaken with pure water, the solubility is found to be 0.64 gram per liter. So this is the solubility that's given to me. Calculate the Ksp of this particular salt. So I know the question is talking about solubility product of this particular salt. Solubility is given to me, again it's in grams per liter. So if I need Ksp, let's first write down what would be the expression for Ksp for this salt. PbF2, which is going to be a solid, will dissociate to produce Pb2 plus ion and 2 fluoride ions. Alright, so now I know Ksp for this particular reaction is going to be concentration of lead ion to the power of 1, exponent of 1, times the concentration of fluoride squared, because my stoichiometric coefficient is 2. So if I can figure out these values right here, this is going to give me my Ksp. Now the question is about solubility. So since it's given to me in grams per liter, I would convert this into molar solubility and use that. If I want the molar solubility, my Ksp expression in terms of molar solubility, I need to know what would be the equilibrium concentrations for both of these ions. So initially I have 0 for each. Change is going to be plus S here, plus 2S for fluoride. At equilibrium, I'll end up with S of this and 2S of this, right? 0 plus 2S. So that means my Ksp is going to be S for lead times 2S squared, okay? Do not forget any of the 2's here, neither the exponent nor this 2. Otherwise, you'll not get the correct answer. So Ksp is going to be 4S cubed. So now if I can solve for S, I can solve for Ksp. How can I solve for S? Let's start with solubility, which is given to me in 0.64 grams per liter. I want this, what is this solubility? This is molar solubility, which is in molar or moles per liter, right? So let's try and convert this into moles per liter. How do I go from grams to moles? I need the molar mass. What is molar mass for PbF2? Molar mass, you'll figure it out using the periodic table of PbF2 is equal to, if you calculate, I believe it's 245.2 grams per mole. So we are going to plug that value right here. So I want to cancel grams, so grams are going to go at the bottom, moles will come on top. 1 mole is 245.2 grams. Grams could cancel, my answer is in moles per liter. That's exactly what I need. So this gives me a value of 2.6 times 10 raised to power minus 3 molar. So this is my capital S right here. So now that I know capital S, I can plug this value into my expression of Ksp, and my Ksp will be equals 4 times cube of 2.6 times 10 raised to power minus 3 cubed, which will give me a final answer of 7.0 times 10 raised to power I don't know what the final answer is. So let's look for the final answer in the final answer slide, which is 7.0 times 10 raised to power minus 8. Okay. Now it's not necessary every time the question will ask you what is the Ksp of this particular salt. It can also ask you what is the concentration of cation or what is the final concentration of anion. So in this case, concentration of cation, remember, is S. Concentration of anion is 2S. So if I know the value of S from here, I can plug that value right here and get the concentration of each of the cation and anion. All right. Okay, let's try another question. Question tells me calcium hydroxide is a major component of mortar, plaster, and cement, and solutions of calcium hydroxide are used in industry as a strong, inexpensive base. Calculate the molar solubility of calcium hydroxide in water if Ksp is given to you. Fairly simple. The question is asking what is the molar solubility, which I know is capital S for this particular salt, and Ksp is given to me. So if Ksp is given to me, I know there is a relationship between Ksp and capital S for every salt. So I'll first figure out what is the expression and what is the relationship between Ksp and S, and then solve for capital S, right? So for this particular salt, it's calcium hydroxide, right? It's going to be solid. It will dissociate to produce calcium ion, which is calcium 2 plus, aqueous, and each salt is going to produce 2 hydroxide ions, right? Each hydroxide ion is -1, which is also aqueous. So this solid is not going to be used in expression. This is 0, 0 plus S plus 2S. Final is S, 2S. So I know my Ksp for this salt is calcium ion concentration times hydroxide ion concentration squared. So it's going to be S times 2S squared, which is 4S cubed. So Ksp is 6.5 times 10 raised to power minus 6 equals 4S cubed. So what is S going to be? I'll divide both the sides by 4 and take a cube root of both the sides, right? That would give me capital S. So in this case, S is going to be cube root of 6.5 times 10 raised to power minus 6 divided by 4, which will give you a final answer, a final number, which we can check in our solution right here. Final answer is 1.2 times 10 raised to power minus 2, right? Fairly simple, right? So now let's try out next question. Oh, this is a question that we have talked about, how Ksp, we can use Ksp to figure out relative solubility or compare the solubility of different salts. So for instance, a question like this, arrange following salts in increasing order of their solubilities. And what's given to us is all of their Ksp values. So now we know how can we figure out in their increasing order of their solubilities. What are the solubilities? Solubility is capital S. Okay, so just by looking at Ksp, you cannot arrange the salts based on their values of Ksp. You first will have to figure out what is capital S, and then based on capital S, we can arrange them in their solubility order. So for instance, the salts that will have a higher value of capital S, meaning they will have higher solubility. And we know how to convert between Ksp and capital S. Now one quick suggestion here is, first thing I would do is I would write down the expression for all of my salts. Okay, it's quite possible that the salts that you get, you might not even have to solve for capital S. Okay, so for instance, in this case, the first salt that I have is AgI. What would be the expression of Ksp for this? So I know it's going to dissociate. Let's try and do this quick, okay, without writing the equation. Ag is going to dissociate, AgI is going to dissociate to produce Ag, which would be one salt, right? Sorry, one ion. So meaning at the end, if you can do this ice table in your head, it's going to be 0, 0, plus S, plus S. S and S, right? So Ag is going to be S, I is going to be S. Why? Because I know I'm doing this in my head, okay? I'm writing it for you guys, but you should be able to do this in your head. S minus, oh, sorry, I minus. So Ag plus and I minus, one of this, one of this. So at the end, it's going to be 0, 0 plus S because it's 1, 1. So SS meaning SS, right? So Ksp is going to be S squared for this particular salt, right? Now let's try to do the same thing for CuI. CuI will dissociate to give CuIn, which will be 1 Cu, so 1 S, 1 iodide, so 1 S. It's going to be again S squared. Last one is calcium sulfate, which will dissociate to give me 1 calcium, so 1 S, 1 sulfate, so 1 S. Ksp is going to be again S squared. So if I want to calculate S for each of these, it's going to be square root of Ksp's, which means for S I have to take square root of each of these KSPs. So either I do that to calculate what is capital S and then compare them, or we know that whatever is the relationship between KSP, the same would be the relationship between square root of KSPs, right? So I can just arrange my solves based on this order, but you should be able to do this to confirm that. Otherwise, the easiest way, if this is confusing for you guys, you can always figure out and solve for capital S and then compare the solves based on that. Just remember, always, whenever you're putting the relative solubility, we are going to be talking about solubility. You cannot just use values of Ksp. You have to use capital S to arrange the salts in their order of solubility. Okay. So one way is you take square root of that, and each of those will give you the same order as the Ksp. So which has the highest Ksp here? This. So this is going to be the most soluble salt, then this, which is CuI, and the least soluble salt is going to be AgI. So essentially calcium sulfate will be more soluble, then copper iodide, then AgI is going to be the least soluble. Okay, and like I said, if you can't do this in your head, you can always calculate capital S for each of these and then compare. See, if I calculate capital S, it's the same exact order. This S is the smallest one, so it's the most soluble, lesser, and then the least soluble. All right. Okay, so why I told you to compare S, you can see an example now. So try to do this by yourself. Pause the video right here, and then we'll come back and discuss this question. All right, so hopefully you guys have the answer for this question now. So in this case, it's the same idea. We'll try to, the question is asking, arrange the following salts in increasing order of their solubilities. So what's given to us are Ksp. Solubility means we are talking about molar solubility. So we have to solve for S for each of these. So let's first write down what would be the expression for them. So again, try to do this in your head, but only after practicing a lot of these salts, okay? So CuS is fairly simple. It's going to produce 1 copper ion, 1 sulfide ion, which will make our Ksp S squared, right? This is a tricky one. So each of this, I'm gonna write it like this from here. Ag2S is going to produce 2 silver ions and 1 sulfide ion, right? Meaning if this is, I will skip the I and C part of the ice table and just go straight to the E. This is going to be 2S, this is going to be S. Ksp here is going to be 2S squared. Remember, it's going to be silver squared times S sulfide, which is S. So it's going to be 4S cube. So in this case, Ksp is 4S cube. Let's try to do the same for this particular salt. So I have bismuth sulfide, which will dissociate to give 2 bismuth ions, right? Oh, and 3 sulfide ions, right? So based off of this, what can I do? This is going to be negligible. I don't care about it. It's 0, 0, plus S at the end. Okay, I'm going to write this 2S, 3S, but if you can just skip and directly do the equilibrium concentration, that's good enough as well. So this is 2S, this is 3S, and Don't make a mistake here. Make sure you write down the expression of Ksp. Don't go too fast. It's going to be bismuth concentration, bismuth ion concentration squared times sulfide ion concentration cubed. Okay, so don't make a mistake. Don't go too fast. It's going to be, so that is going to be 2s squared times 3s cubed. Okay, that would give you 4s squared times 27s cubes, which would be 108s. Whenever you have exponents, remember, if it's the same, you can always add those up. We have discussed this before. So this is s squared times s cubed. Whenever they are in multiplication, you can always add the exponent, so that becomes, don't end it, 3 plus 2, which is 5, 108s 5. So here Ksp is 108s to the power of 5. So we are going to use these to calculate our capital S or molar solubility values, which would be S equals square root of Ksp. S here would be equals Ksp divided by 4, and it's going to be cube root of that. And in this case, it's going to be Ksp divided by 108, and we'll take the root to a power of 5 of that. All right. So once you have solved for these capital S, it will give you these certain values, which is right here, solved for you guys. So now once you have capital S calculated, you can compare these values to figure out which one is more soluble compared to the other one, right? So in this case, see that which one is more soluble right here. This has the least highest solubility, so this is the most soluble, followed by silver sulfide, followed by copper sulfide, right? So if you were doing this right here based on just the Ksp values, see how the Ksp values do not follow the same trend. So just make sure that whenever you're comparing the solubilities of different salts, you're comparing their solubility in terms of molar solubility and not just the Ksp. Okay? Ksp is needed because you're going to figure out their capital S values based on the Ksp, but just don't go straight comparing the Ksp values, right? Okay, so that's your final answer. And now let's talk about another concept when it comes to solubility of salts, which is common ion effect. So up until now, whatever salt solutions we were making, they were all being made in pure water. So all our calculations were being done in when we were trying to solubilize the salts in pure water, right? So a solvent was just water by itself. Now what happens if instead of using pure water as our solvent, we are going to use another solution as our solvent, okay, which already has some of the ions present in it. Okay, what do I mean by that? Let's look at one of the very common examples. So for instance, right here, let's assume this solvent in here that is present is water plus PbI2 solution. So this solution that you see right here, forget about the yellow precipitate that you see forming. So before addition of any of the precipitation being formed, let's assume this is a solution, a saturated solution of PbI2. So lead iodide. Okay, this lead iodide is an insoluble salt which usually has a color of yellow, right? So initially when we just have a saturated solution, what it's going to look like, it's just going to be a clear solution of PbI2 in water, right? It's saturated, so meaning at this point, if I add any more lead iodide into this solution, it's not going to solubilize and I'm going to see some solid precipitating at the bottom, right? So what is here in the solution on top that we are mixing? This is a potassium iodide solution. So this is a very classic example. When we add any potassium iodide into clear saturated solution of lead iodide, some of the yellow precipitate starts forming. And what is this yellow precipitate? This yellow precipitate is lead iodide. So if we mix a saturated solution of lead iodide with some potassium iodide, it is going to precipitate some of the lead iodide out. Why is that? This can be understood by the common ion effect. This is essentially a variation of Le Chatelier's principle that we have seen before, right? So assuming we go back to our Le Chatelier's principle, so assuming I have PbI2 saturated solution, it's going to be in equilibrium with the ions, which is cation, lead ion, and anion, iodide ion, right? So what does Le Chatelier principle tells me? It tells me that if I add any more of the products into my solution from outside, which direction will the reaction go? If I add any more iodide from outside into this equilibrium solution, the reaction will try to decrease the amount of iodide. And how can it decrease the amount of iodide? It will use up the extra iodide that we have added from outside, and it will shift the equilibrium towards our reactant, which in this case is PbI2, which is solid. So when we are adding some potassium iodide into the solution, what is potassium iodide? Potassium iodide is a soluble salt. It consists of two different ions, which is potassium ion and iodide ion. So when I'm adding a solution of potassium iodide, I'm adding some more potassium into the solution and some more iodide into the solution. And when I add more iodide into the solution, my Le Chatelier's principle tells me that the reaction is going to shift, the equilibrium in the reaction is going to shift towards the reactant, which means it is going to produce more solid lead iodide, and that's what you see right here precipitating out, as it precipitates out as a yellow solid, because lead iodide is yellow in color. All right, so this is for a solubility product expression. This is given as common ion effect. And I already explained you the reason behind the common ion effect. Why do we see that? Because this is based on how equilibrium works, which we understand already based on our Le Chatelier's principle, right? So let's say if I'm looking at another example now, in this case, there is an equilibrium between lead chromate. It's a saturated solution of lead chromate, which means that there's an equilibrium between the solid lead chromate and the ions, which is lead ions and the chromate ions, right? So now if from outside I add a solution, let's say I add some right here, let's say I'm adding some sodium chromate into the solution, which means when I add some sodium chromate, which ions am I adding? I'm adding some sodium ions and I'm adding some chromate ions. So if I add more chromate ions, which is a product here, which direction will the reaction equilibrium shift? It's going to shift towards the solid lead chromate. So you will see after addition of some sodium chromate, it will start some more of lead chromate is going to start precipitating out. So see, initially we had this much amount and now there is some extra amount of lead chromate being precipitated out. And why is this happening? This is happening because of the common ion effect, which means what is the common ion here? The ion that is common between the salt, insoluble salt, and the solution that we are adding from outside. So in this case, it's the chromate ion because our salt has chromate and the stuff that we are adding from outside also has chromate. So the common ion in this case is the chromate ion. And what is the common ion effect? What is the result of this effect? Essentially, it is lowering the solubility of the ionic compound. So whenever I'm going to add any of the common ions into a saturated solution of salt, it is going to precipitate out. Precipitating out meaning initially it was all soluble, but now since I've added more stuff from outside, its solubility is different. It has lowered down the solubility of that particular compound. So common ion effect essentially is whenever you add a common ion into a saturated solution of an insoluble salt, it will lower down the solubility of that ionic compound, right? So that is the common ion effect. Let's try a couple examples in this case. Couple question. So what effect would adding copper nitrate have on solubility of copper sulfate? So what am I adding? I'm adding copper nitrate, which is a soluble salt, and it's going to add copper ion and nitrate ion. on solubility of copper sulfide. So if I have a copper sulfide solution, common ion, without thinking, it's going to lower the solubility or decrease the solubility. So right now the saturated solution I have is copper sulfide, right? Will consist of copper ions and sulfide ions. What am I doing? I'm adding copper nitrate from outside, which is my common ion now, copper. I'm adding more copper. The reaction equilibrium will shift towards the reactant and the solubility would decrease. So my answer is B. You should be able to identify which one is the common ion. So the answer is the solubility would decrease. Okay. Now we have this question right here. Let's try to solve this particular question. Consider three cases. What is the molar solubility of silver chromate in pure water? What is the molar solubility of silver chromate in 0.1 molar silver nitrate solution? What is the molar solubility of silver chromate in 0.1 molar sodium chromate solution? All right. So up until now, we were solving all the questions in pure water. So let's try and work out problem number 1, which is part A. You should be able to solve this question without any problem. Ksp is given to us in question. The question is just asking what is molar solubility, which is capital S, in pure water. So whenever you have solution in pure water, that's fairly simple. You can write your equation, which is right here. Ag2CrO4 is going to dissociate to produce 2 silver ions and 1 chromate ion. Initially, this is going to be, oh, sorry, we don't consider this. Initially, this is going to be 0, 0, plus 2s, 1s plus s, sorry. That would give us 2s at the end and s at the end, right? So what would be my expression of Ksp in this case? Ksp would be concentration of silver ion squared times concentration of chromate ion, right? Which would be 2s squared times s, which is 4s cubed. So what is s? S is going to be Ksp divided by 4 and cube root of that. Simple. We've done this question way too many times now. So from here we can solve for s. We know the value of Ksp, so it's going to be cube root of 1.1 times 10 raised to power minus 12 over 4, and that would give you a final answer. Okay, easy. That is when we are talking about Ksp of this salt in pure water. Now we know we are making this salt in a silver nitrate solution. What is common in this case? We see our saturated solution as silver and chromate, and we are making it in a silver nitrate solution. So silver here is the common ion. And what do we know? We know that common ion is going to decrease our solubility. So let's confirm if that would make sense with our numbers as well. Okay, so now what we are going to do, let's work on problem number B. So whenever question is given to you in exam, of course it's not going to be part A, part B, and part C. Any one of these can be given to you as separate question, right? So you should be able to identify what kind of solution it's talking about. Is it solubility of the salt in pure water? If it's the solubility of a salt in a common ion solution. Okay, so let's try question number B. Okay, so let's try part B. What is molar solubility of silver chromate in 0.1 molar silver nitrate solution? So I already have a solution of, what is the question giving me? It's giving me Ksp value, and it's telling me that my solution is 0.10 molar silver nitrate, which means I already in my solution have 0.1 molar silver ion and 0.1 molar nitrate ion, right? Because silver nitrate will completely dissociate to give a silver ion since it's completely soluble, and nitrate ion, right? So it will have 0.1 molar of this and 0.1 molar of this. Now, since it already has this, it's going to change our ice table. So in case of our ice table now, we don't care about this. Instead of using a 0 initially, now our initial concentration is going to be 0.1 molar. Since this is our common ion, we already have 0.10 molar of silver. Nitrate, we don't care since it does not exist in this particular expression. So we only care about the common ion. Chromate, on the other hand, is 0. What would be the change here? It's going to be plus 2s. This is going to be plus s. So at equilibrium, this will be 0.10 plus 2s and s, right? Now this is our ice table, and we know Ksp now is going to be equals silver ion concentration squared times chromate ion concentration, which is 0.10 plus 2s squared times s, right? Now we have to solve for this. Again, it's a quadratic equation, right? The same rules that we use whenever we are solving a quadratic equation for equilibrium are going to apply right here. How do we usually solve a quadratic equation like this? We want to simplify this for us, so we are going to make our assumption. So in this case, since our Ksp is a really small number, 10 raised to the minus 12, we can assume that the value of s is really small, meaning 2s is really small. So we can assume that 0.10 plus 2s is same as 0.10. So now our expression for Ksp will be reduced to Ksp equals 0.10 squared times s. Right, now we are just going to use this to solve for s, which will be Ksp is 1.1 times 10 raised to the power minus 12 equals 0.10 squared times s. So s is going to be 1.1 times 10 raised to the power minus 12 divided by 0.10 squared. And if you solve for this, this would give you an answer of 1.1 times 10 raised to the power minus 10 molar. Okay, this is minus 10. So now that I know my S, what is the answer? The question is asking what is molar solubility. The question is also asking for S, so this would be my final answer. Right? The question could also ask what is the final concentration of silver ion at equilibrium and what is the final concentration of chromate ion in equilibrium. In that case, how will you solve this? The final answer, final concentration of silver ion is going to be 0.10 plus 2s. So we're going to plug this value in, calculate that answer, and final concentration of chromate ion is going to be s. Okay, this question is not asking that, but in case it does, you know how to solve for it. Okay, now let's try part C. Hopefully this made sense. Now we're going to use the same idea to solve for part C. So you can pause the video right here, try to solve for C, and then come back and look for the explanation and the final answers. Okay, so now let's try and solve for part C. What is the molar solubility of silver chromate in 0.10 molar sodium chromate? Ksp is given to us. So what is the question asking? Question is asking molar solubility, which I know is capital S. Ksp is given to me, so if I can figure out a relationship between Ksp and S, I can solve for S. But what I have to remember here, that now I'm preparing the solution in a common ion solution. And what is a common ion in this case? It's chromate. So if in the beginning I already have 0.1 molar chromate. How do I know that? This ion, or sorry, salt is going to dissociate to give me 2 sodium ions and 1 chromate ion, right? So if it has 0.1 molar, it's going to produce 0.10 molar of chromate and 2 times 0.1 molar, which is 0.2 molar of sodium. But I don't care about sodium because that's not my common ion, right? But you should be able to understand that, right? Because each of the salt is going to produce 2 sodium ions, so the concentration is going to be twice. Okay, all right. So anyways, coming back to our question, I do not care about the solid. Initially, I don't have any silver, but I do have chromate, which is 0.10 molar. This is going to be plus 2s. 2 comes from the stoichiometric coefficient. This is going to be plus s. So my final equilibrium concentration is 2s for this and 0.10 plus s for chromate. So what is my expression for Ksp? Ksp is silver ion concentration squared times chromate ion concentration, which will be equal to 2s squared times 0.10 plus s, right? Now again, this comes, I can plug in the value of Ksp here, and this comes down to quadratic equation. So I can simplify this equation by assuming that Ksp, which is 1.1 times 10 raised to the power minus 12, equals 2s squared, which is 4s squared, times this is same as 0.1, right? 0.10. So that would give me 0.40 s squared. So my s would be 1.1 times 10 raised to power minus 12 divided by 0.40 and square root of the whole thing, right? So that would give me my final capital S, which is molar solubility. So let's confirm our final numbers. Oh, right. So here are your final numbers. If you solve the way we did, it should give you a solubility of 1.66 times 10 raised to the power minus 6. This is your final answer. You just have to give me this number. You do not have to solve any of this out. This is just extra information for you guys. So this is your final answer, okay? And you can stop right here. But if the question asks you, what is the final equilibrium concentration of chromate ion, final equilibrium concentration of silver ion, that's when you try and do this extra step, right? Because this is S, concentration of chromate is going to be 0.10 plus S. So plus this, which is really negligible. If you come it down to the number of sig figs, the right number of sig figs, it eventually will come out to be the same number. And silver is going to be 2s, so 2 times this number will give you 3.3 times 10 raised to the power minus 6, right? Okay, so that was about that particular question. Let's try another question right here. So what have we learned based on this? We just saw that when we have silver chromate ion, we dissolved it in pure water, the solubility was this. And you solve these numbers right now, right? When we dissolved it in silver nitrate solution, solubility was this, which is lower than the initial solubility, right? So this is common ion effect. The solubility is lowered if we have a common ion in the solution. Same thing if we dissolve it in sodium chromate, which already had a common ion, which is chromate. See, the solubility was decreased as well. All right. So in both these cases, you can see the solubility is actually decreasing as we include the common ion. All right. So there's another question for you guys. It's based on a very similar concept. So I'll let you guys try it first. What is the question is asking us? It says calculate the solubility of calcium hydroxide in a 0.1 molar calcium nitrate and compare it to the solubility of calcium hydroxide in water. So same concept. We want to calculate solubility of calcium hydroxide in calcium nitrate. So first figure out what is capital S in this. Then compare it to solubility of calcium hydroxide in water. So we'll have to figure out what is capital S in water. So same concept. We figure out two different calcium hydroxide solubility values and compare those, right? Ksp is given to us. So I'll pause the video here and work on the question by myself, all right? And then you can come back once you're done and look for the explanation and final answer. All right, so based on this question, what's given to me is the Ksp value. The question is asking S, so I have to calculate two different values of S. First is in calcium nitrate solution. What is the common ion in this case? My salt is calcium hydroxide, so my common ion is calcium, which means to begin with, I will have some calcium in my solution. So my initial is going to be 0.10 molar for calcium. And I can create the table based off of this. So right here, the initial concentration of calcium is 0.10, hydroxide is 0, plus S plus 2SY because it's two hydroxide ions. So it gives me 0.10 plus S, 2S. Ksp is concentration of calcium ion times the hydroxide ion squared. So I'm going to plug in my values right here. And remember, I'm going to make an assumption that 0.10 plus S is same as 0.10, and that would help me simplify my equation, and I can solve for capital S. So that gives me a value of 4.0 times 10 raised to power minus 3. Now the second part wants me to calculate this in water. If it's pure water, I do not have any of these ions to begin with. It's going to be 0, 0 for both initially, plus S, plus 2S, S, and 2S, which means my expression for Ksp is going to be calcium ion times hydroxide ion, S plus times 2S squared, which would give me 4S cubed. Plugging in the values of Ksp and Ksp, I can solve for capital S, which comes out to 1.2 times 10 raised to power minus 2 molar. So essentially, I have figured out what is the concentration or the solubility in presence in water and in presence of a common ion. So you can see again here, in presence of water, it was 1.2 times 10 raised to power minus 2, and it decreased when we have a common ion, right? So these are the kind of questions you can expect in exam from the common ion effect and solubility product of a given insoluble salt. Okay, I'll see you guys in the next lecture video.